So parametric design essentially it means instead of considering only one design, we consider a whole range of designs which are characterized by different parameters. So I have my design up as a system, right, which is thinking of BIM. Yes, we have these objects and they transform. So now if I have my whole building set up as something that's defined by a range of numbers ultimately, then I can say, okay, I can now run through a lot of different iterations. Right? And that might be good, for formal design. So now I can just quickly look at different options and see what I like better, and also helps me to make more complicated things. But it also helps with this other aspect of automation. So once I have this ability to automate things and have programmed things that are rule-based and that are programmed, I can just automate things that are boring. Right? So I can quickly exchange drawing blocks, for example, or I can even make drawings automatically of certain elements that are repeatable. Right? So there are certain tasks that come up in daily life that are actually quite helpful to automate. And then the last dimension would be, well, since we are already working like in this systemic way where we work with numbers and values and parameters, then it becomes really natural to include some performance analysis as well that's driving our changing system. And so these are, you see these three dimensions, and then we usually say, well, so usually you're somewhere in between, right? So you usually do some combination. So maybe it's a little bit automation, and then maybe there's some performance aspect, or there's something that looks really interesting, but it also has some performance aspect. And so, so this is kind of the space we're moving in. And so just as an example, I'm going to talk about a project that we did about 2 years ago for Adobe Got Green, so really right outside of our window, which was a competition by SIA for Parametric Pavilion. So it was really an ideas competition, basically asking, make something that showcases what parametric design is for and what it's about. And so this was the winning project. And maybe the first thing that's remarkable about this is that there's lots of diagrams, right? Lots of information, and actually very little like right architecture. So there's some drawings here and some pictures here, but really it's a lot about process. And so basically we have sort of 3 steps. So we have on this side we had sort of an urbanistic idea about looking at the different pathways we might take over Adobe Got Green, and then all the different variants that come out of that, and then finally settling on one variant, right? So this is like really this idea of parametric design. So I have lots and lots of different variants, and then we get onto this world which has there's a performative idea, and basically so we look at the structure, we look at solar radiation, we look at the program, and then we have this idea of the pattern skin. So the facade of the pavilion has different densities, and the densities respond to the structure, to some solar considerations, and to the programmatic considerations. So now just to see this a little bit in more detail, right? So here are some path systems which are formed according to some rules. Now, it's actually a little bit of funny details of what are the rules. We made this by using SOAP. So this is usually you think, oh, parametric design is in a computer, but really we can. Right, SOAP film is also some natural phenomenon which is very rules-based. It's about minimizing the energy of the SOAP film, so we're dipping our model into the SOAP, and we were looking at the different SOAP film configurations to study these, and because what we get is not only minimal energy SOAP film, we get also minimal path length networks that are connecting the different points across the site. And okay, so this is a bit of fun part, right? And then we did this whole study here where we said, okay, what happens now if we apply the program of this pavilion onto these path systems? And then we had a scoring system to actually decide between all these different variants. Okay, so this one is better in terms of the shading, but it maybe has a longer path, and this one fits the program not so well, but it has some other good qualities, right? And so then we settled on one basic variant, and then we made another study of another 10, again this criteria, saying, okay, why is this good, better than the other, and again this is a scoring system. Finally settling on one thing. And so then we get the second part, which is about how we modulate the pattern. Right? And so the idea is, up here we have a structural analysis. So we're looking at the displacement and said, okay, where the pavilion is deforming the most, which is here the areas in the roof. It's very logical because the shape is a little bit flat on the top, so that's where it's sort of deforming. The pattern should be very dense in these areas. That's one consideration. And the other consideration, they're looking at the solar irradiation and just say, okay, how much sunlight do I get on average over the year in the different places of my design? Again, it's a very logical result that you get a lot on the top and not so much on the sides. And then lastly, we came up with this, which is not a part of an analysis, but this is like something architecturally defined, which just is painting the values that we want architecturally. So saying, okay, it should be very open in the middle here, because that's where people look into the courtyard. Here, this yellow area, that's a stage, so the stage should have a closed background, so it's very dense here. There's a library over there, or an exposition over there, which should kind of a medium openness. And then we combined all these into this final diagram, which says, okay, this should be the density of our facade. And then, right, now we get really the automation part. So we had this, and then we also had these different pattern tiles of the pattern. And then we could automatically say, okay, now please apply this pattern according to this density configuration, ending up in this final design, which had like this pattern which has two levels, like the more detailed pattern, which is only making shading, and then a sort of larger scale, which is structural. We did one validation step, which is this one. So this is then really looking, okay, right, because earlier we were looking at how much sunlight is hitting my pavilion and how much light would I want inside programmatically. This one is saying, okay, how much daylight do we now actually get, given that we have this pattern facade. And what you can see is that it's relatively close to what we intended programmatically. So it's actually the case that, for example, the library has a little bit more light than the expo, and the stage a little bit less. And so this is not really trying to be very scientific, but at least it's showing, okay, so the general idea actually works, and now if you wanted to, you can go in much more precisely and get this really to work. So right, we end up with something that kind of looks like that. So we have it's very dense on the top, it's more open on the sides, and it's right. So this is a stage area where it's more closed. Here, more grill, it's very open. So I think you can really see that there's actually an effect here, and that it's not just some architecture playing around. And then, of course, on the inside, but ultimately what we really were going for is to have these nice shadows, right? To have this play of light and shadow, like being in the forest, so hoping to have some very interesting lighting conditions. Okay, and so now this, for now, right, this is all very theoretical, and in fact, this was even never meant to be built, and in this stage would also be very difficult to be built, right? If you look at these connections, how would we do this? Which was not right there, because the competition made something parametrically, which then, for instance, okay, let's make the most complicated thing that you can think of. But then, actually, there is a further development of this, which is this wall screen here, which was exhibited at the NDC last December. And so, as you can see here, we have developed the system a little bit further. It's not these single elements anymore, which come together in horrible ways, but it's actually components, and we can so we have triangle components, and then we can cut the pattern out of a flat sheet. And now the interesting thing is that all of these components are different, right? Both their shape is different, and also their pattern is different. And again, right, you have a parametric system behind this, so we basically have the shape, and then we automatically can generate the geometry of these components. And not only that, you can also automatically generate those, which are the cut sheets, which go to the machine. And so really the only thing that is left is to be done is to fold the thing, assemble. And because all the components are different, you also don't need a drawing, because it's like a puzzle. There's only one way to put this together. So just here's a little bit the machine. It's a company in Singapore that has this giant laser cutter where you can really make building size components, or at least sort of in between, right? Larger than a model, maybe it's still a little bit smaller than a building, and that can directly take the inputs that we're generating, cut it out, and then we have a machine back at our university, fold it. And so, right, and so there's a there's a continuity in terms of this workflow that we can directly go from our model into actually making something. And in this case, we're actually skipping the documentation phase, right? We go directly from design to construction. And now this has even a further story, a big version, which we are developing right now, which is hopefully actually going to be completed this year. It's not been officially announced yet, so I can't say too much about it. Just to show a little bit how this looks like on a bigger scale, and also just to show how this is not, how this yes, it is kind of a special application thing, but it does lead in some cases to like architecturally valid proposals. And so, right, so the idea being to show you, right, so we've seen a little bit the different dimensions of what we can do, right? We can design complicated things, but we can actually also make them, and we can also simulate and take performance things into account, and then also use it to manage like complex architectural shapes, like this one. And so before I show you some more practical, like a live case study of parametric design, let's see if there's any questions about this first part.
Do you mainly do your modeling, I guess, do you sort of maybe Python programming aside from just parameters, or do you generally just use components?
You mean what are we using? Are we using Grasshopper or Python?
Yes.
Right, so basically it's a good question, because there's two, because now if we look into how are we actually doing this parametric design, there's two paradigms. And let's actually just have a quick look at these two. Right, so we tend to use Rhinoceros as our platform. Let's maybe get into why. But so one paradigm is the Grasshopper paradigm, which is now there's a Grasshopper-like program also for Revit called Dynamo, which is very similar. Just similar the idea. So what you do in Grasshopper is you basically have this thing called a canvas, and then we have all these little icons, and we can drop them onto the canvas like so, and then we can start connecting them like this, which is actually programming, right? Because what I'm basically doing is something happens inside of here, and then there's an output, and then I run the output into something else, right? So it's basically every box is like a little calculator. Something happens in the box, and then I can network my boxes into very intricate ways to make complicated things. And so underneath of this is like a program that you're making, right? But to make it sort of more user-friendly, instead of the program, you see this graphical representation, representation. Now the other thing, and that was the question about the Python. Oops. So Rhino also comes with just a programming interface, which looks like this, right? So same goal, same parametric design, completely different way of doing it, just by writing in text, and also based a little bit on a different, it's a different way of interacting this software. So in Grasshopper, we work with these components. This Python program is using something that's called Rhino script, right? And so Rhino script is just, let's say, a programming library that is available for different programming languages. But nowadays, the popular one is Python, and so it just has all kinds of things. Basically, and usually things are very, right? It's almost like if you type into AutoCAD, right? To add a line, you type a line, to move a point, there's a move command, and so on. Okay, and so what we do both of these things. And we also mix them together, because you can, in fact, well, you can have a Python box in Grasshopper. And so now I'm going to go back to the Grasshopper. Oops. Under mass, there's the C#, the Python, and the VB, where you can have a little box, and then the little box itself is a program. And so and why would you want to do this? There are certain things available in Grasshopper that are not available in Python, and the other way around. That's a good argument for mixing the two. And also, the one thing, Grasshopper is very nice because, as you'll see in a minute, in Grasshopper you change something, you immediately get a visual feedback. It changes. You have sliders, and you can see a model change. If you have a Python script or a Python program, that's not true. You just run the program, you see what you get. If you don't like it, you rerun the program. But there's no live update. But by putting my Python into the Grasshopper, I can have a live update. Okay, I think that was maybe already a little bit technical. More questions about but if you have questions about this whole Grasshopper, Rhino, Python affair, you can also just go into the case study and then you just see a little bit more how it's actually working. All right, so maybe we do that. Okay, so I'm going to show you something. But as I said, we do these workshops, and so I'm going to show you something, so a simplified case study that we use in our workshops. So we have a simplified urban context, which are the boxes, and then in the middle here we have this form, which let's say it's some kind of roof, right, for maybe a hawker center or a market or a performance space. And what we want to do is we want to have some paneling for this roof to modulate the sunlight. And so I have already a Grasshopper thing prepared. This is a little bit like a cooking show, where I always have to put out different kind of things. So this is now a classic Grasshopper definition, right? Which immediately looks very complicated, right? So because there's all these boxes now and they're networked in different ways, and so that's also like, personally, if I want to make something complicated, I prefer to program it, because this, even though it looks very complicated, at the end of the day, it's not doing very much, as you see. So you can get lost in this, right? Because in the beginning, it's very easy to drop things on and to connect them, and it's a lot of fun, but you can work yourself into a mess. While the computer program is going to be more strict and more painful, but automatically it's harder to make a mess. Okay, so what's happening here? We are doing we're doing the classic parametric design example. So which means we have these folded panels which are mindful of the esplanade in Singapore. But the trick is, right, we have already distributed them over the surface, right? So that's something, and that's like something that's actually very straightforward to do, right? We have this irregular shape, but at this point I already know what the shape of these triangles should be and where they are located in space, which is a useful thing. And right now, because it is parametric, I have, for example, here two input parameters which define how many parameters I have, right? And because it's a live update, oh, sorry. Now I can pull my slider and can look, right, we can get sort of, now I made a lot of divisions. Let's make 4. So we can, right, we can, so that's like, we can play with our design, right? And that's a very simple example, but I think just to give you an intuition of what we might do. So that's one nice thing. And then the other nice thing is that, so not only can we play with our sliders, we can also play with our input shape, right? So I have this input of the so-called control curves, which relates to some curves I have here in Rhino, right? And so now if I move in Rhino, right, I move this element, voila, the loop is changing, right? Which is again a very useful thing, right? Say you're working on this groove and you have developed this whole fancy geometric model and suddenly the shape changes, right? If you have say you have modeled this in Revit and the shape changes, then you have to remodel it. That's very painful, right? So here it just changes for you, right? So that's beautiful. As long as you have guessed correctly the thing that will change. So that's sort of the basic story, right? We can make things automatically, we can change, it follows. And now let's go a little deeper. Right now, you can see they all basically have sort of the same degree of openness, these facade panels. Right? So the next thing I might want to do is to sort of adjust the opening angle to address different considerations. So a classic idea that we often use is the so-called attractor point. So there is a point here, and the degree of openness of these panels changes according to the distance to the point, which again is basically just a way of building a design machine, right? So now, as the architect, I can just move this point around and see my design change. And so again, basically quickly explore different options. Let's see, let's change it. No. Right, so again, this whole idea, so I have some instead of designing directly on the shape, I have defined some system around it, right, which is some control curves and some attractor point, and now I'm just manipulating the system, and in this way I can much more conveniently sort of iterate through different options. All right, so now we can sort of go to the next stage and say maybe this should actually be informed by some performance consideration. So we're gonna do the same thing that we did for Dobigod. So we can do inside of Grasshopper actually a solar irradiation analysis, and then that will determine what these facade panels are doing. So here is the solar irradiation part, which I need to enable now. And tell him to actually run the simulation, right? So now he's accessing some outside program to run the simulation. And now we can already see right, so this is the result of the solar irradiance analysis, which let's see, yeah, which sort of takes into account the context, right? So there's very little light on these sides here where the surrounding buildings are, and then there's lots of intensity of light over here where it's open, which we get into beautiful representation of the false color map, and then hiding this again. Right, and so the logic is it's very open where there's not so much light, right? So when the area here where we saw that's very bright, it's almost completely detours, which would make sense, and the areas in the front where we know there's going to be less light, it's more. Right? And so, but previously what we did with the factor point, just sort of assigning some openness according to the design intention, we can also give this some more valid reason by, for example, running an analysis. All right, so we've covered how we make a design, we've covered how to make it performative, and now I'm going to go into the last section and think, okay, how am I now going to get this into Revit? Because that's a very practical question, but this is like something that we all get a lot, and it's kind of a difficult thing, in fact. But there's one way. Yeah, so philosophically, let's see. So from a theory standpoint, there is really no way to go from Rhino into Revit, because it's just two completely different paradigms. Rhino is not a BIM software, Revit is a BIM software. Which means in Rhino, right, a box is just a box, it has no meaning, no behaviors, right? In Revit, things have like meanings, right? There are columns and doors and windows and floors and grid lines, etc., etc. But in Rhino, that doesn't exist, right? Everything's just a thing. A line is just a line, and how would Revit, right? So so it's like let's see, it's like imagine Rhino is just a table with numbers, and Revit is a book. Right, so you can read the book as meaning, and you will never get from the numbers to the book because it's just a deeper level of meaning. Okay, so what we do instead is we do kind of a hack, and we send some numbers from Grasshopper into Revit, and then we give the meaning inside Revit. Or we can tell Revit what meanings we intend, right? So we can say, I'm giving you these numbers, and I mean they are all columns. Right, for example. So that's something you can do, and I will show you how to do it. But that so that's a good way to exchange specific things. Like for example, this works great for our roof because we are only interested in these roof panels. It doesn't work so well if you have a complete building, right? Because you have to explicitly state everything. These are my floor plans, these are my columns, these are my facade elements, right? So, which becomes a bit painful. Okay, but now, so how does it work? So I have here this thing called the Revit export, and I'm using a plugin for Grasshopper, and the plugin is called Hummingbird, and the plugin has all these types of things, right? It has beams, columns, rows, walls, adaptive components, families, lofts, mass families, which all relate back to things that exist in Revit, right? So now, right, I know I want to give Revit an adaptive component, so I'm giving the points that define these different elements that we've seen. I'm running that into the adaptive component thing, and then hopefully we will somehow shift this into Revit. So so we're only giving points to Revit, right? So in this case, we give like always like the 1, 2, 3, and 4 points for every element. So we actually don't give the surface, and we don't even tell how things are connected. So how can this even work? And the reason this works is because I have already again prepared something in Revit. Oops. Namely, I have prepared this adaptive component in Revit, right? So I've drawn this thing in Revit, which is again defined based on 4 points. And let's see if I do this, right? I move the point and this thing changes. And the good news is these things are numbered, so I know also exactly, okay, so the first point should be this corner back there, and the fourth point should be the tip. So that's something, right? So the input in Grasshopper is already geared towards using this, and so that's how the magic happens, right? So in Revit, I have already defined how I want this component. Grasshopper says the different coordinates and how wide things should open, and then like that, and that's how we create our model. So let's do it. So I create an empty file, and then I'm going to insert this adaptive component that I just showed you into this file. Okay, so now we're ready on this side. So I have this hummingbird thing that exists both as a plugin in Grasshopper to put things out, and it again sits into Revit to interpret the information and to draw it into Revit. So now we first still have to generate the outputs here. So I'm going to do that now. This is the false true. Right, so now I've taught it to write this data out, and in fact we can look at it to check what has happened now. Should be there. No. I know. Because so it's basically just writing out a file, and he's writing the file out to a specific location, and I didn't change the location. Okay, so now he made this file, which is an Excel file called façade panels. Or to be very precise, it's CSV, comma separated value file, but it can be read by Excel. Right, so it looks like this. Right, and so here's the name of the thing to define what it is, and then just a list of the points, right? And then so point 1, first point, second point, third point. So it's a good way to kind of check for us what we're doing. Also, just a good way, I think, to see how this works. And so, in fact, this, so it's nice of Hummingbird to do this for us, but really we could also just directly write this Excel sheet out, right? Because we could have a computer program that just makes this. The more important part is on the Revit side that we actually read this back in. But again, what this really is, so somebody has conveniently programmed something in Revit for us that automatically draws these things now based on the coordinate list. So let's do it. So I want to create elements from a file. The file is it's this file. That's all good. I want to use the Esplanade family. That's exactly right. Oops, unable to connect this. Yeah, okay, because I have. So he's drawing it, which takes a while because he just needs to draw on these adaptive components. Right, done. Let's go to 3D view. Right, and there we are. That's pretty neat. And as you can notice, these actually have a little thickness, which the Grasshopper model didn't have. Right? Because we are defining also on the Revit side, now on the Revit side we can add more information to this. Right? Because maybe we know something about, I don't know, little connectors or some connecting structure. Right? Because we're just sending over the geometric information, so we now can have our Revit model, which is now parametric, be informed by what it's getting from Grasshopper. So that's neat, and which is, I think, the neatest thing about this is now we in fact have established a real link between Grasshopper and Revit in the sense that if I now change things back on the Rhino side, I can get the same update back in Revit as I show you now. Right, so now say we change our divisions. Maybe just change the shape. Right, so okay, simulation is recalculating. The roof has now changed the shape. We move facades. Now I need to make sure that he's actually overwriting this table that we've been using. And now I can go back to my hummingbird here, and now I can tell him to use this option, because he has sort of numbered these elements and he knows what they are. So I can tell him get rid of the first panel and put the new first panel in. So essentially updating it, right? Which is what's happening now. So not exactly live update, right? But close to it. So, and as long as you have like your file names and your paths, your file paths and like the names of things, as long as that's consistent, you can actually have a continuous workflow from one to the other. Okay, so that was a little bit. So that was the easy case study, and now I'm just going to show you also something a little bit more complicated, which is just going back to this wall screen. I just want to show you how this actually looks as a live demo. Right, so we have this as an input geometry. So this is just a little piece of this wall screen, and then we have these numbers sitting on the corners of these triangles, which define what the pattern should be. Specifically, it's basically relating to the density. So if you see a number 4, it means it should be very dense. If you see a number 1, it means it should be not so dense. And because we have two sides, the first number refers to the front and the second number refers to the back. So what's nice about this is that we can, you can quickly change the density values and without remodeling the whole thing. And in fact, this is also what we're now, the same system we're using now on the big pavilion. So we're going to have a mesh. Again, we can have two meshes, inner mesh, outer mesh, defined in fact together with a structural engineer. So the structural engineer can put his structure in between. And then we're gonna, again, have numbers to drive the pattern, and the numbers, again, we're basing on soil analysis, some considerations about the wind, where it should go in and out, and also just some programmatic, like some inputs from the client, we want to close this area, some inputs from us, we want to rather not see this. And so, again, right, we have this very simple setup of having a mesh that defines the shape of the geometries and the numbers that define some density there, but that allows us to very easily accommodate a range of different considerations. Right, and so now to draw my components, I have this Python thing which I referred to earlier, right? So this, because this is a more complicated thing, and also because this is like a very serious thing that should be built, I rather program it than, personally I'm just more sure that what it's doing is actually correct and it's giving me the right thing. So if I run it, it will just say, oh, select the mesh. Okay, I click the mesh, select the dots, I select the dots. And then he will automatically draw the components, and he will also automatically lay them out. And so he's labeling them according to the position. He's drawing the bolt holes in the right spot. He's drawing the green line, which is the line for the packing, because we know on the sheet we need a certain distances between those elements. So the green line makes sure that we actually are following these distances, and so we get both types of things, right? We get the completed screen, how it should in fact look like, which has again already all the detail of how this is actually going to be like built as a folded component. But not only that, we also get it in the plane, and right. So this like this is basically the only way to do a project like this, right? Because I mean nobody in his right mind would want to draw this. Let's see. Oh yeah, so the one thing this does not do, it does not automatically nest it on the sheets for the laser cutter. So that is something that's actually a little bit complicated to do, but so now we have purchased the software that can do it. So hopefully for the big roof, we will have a fully integrated thing that will actually put the bed side, that will already automatically package to the bed size of the machine. All right, so that was it in terms of our hands-on case studies. Yeah, if you have any questions, please feel free to ask. Also, you can ask Aloysius, who didn't have a chance to contribute yet. Otherwise, we're also always happy to hear from you and to see how we can help.